Hello everyone and good afternoon. I am Loic Henriet. I'm a CTO and Managing Director at Pasqal. What I want to share with you today is not a promise about the future of quantum computing, but it's a report on what we've already built. This is our vision, and I'll tell you about how this has translated into reality. Let me first start with where we come from, because it explains about why we're confident about where we're going. So Pasqal was founded on a scientific lineage very few companies can claim. As co-founders, we have Professor Alain Aspect, Nobel Prize in Physics in 2024. We've also the first experimental demonstration of trapping of single atoms that was demonstrated by Georges-Olivier Rémond in 2001. And also Antoine Brauer's pioneering work on the Rydberg blockade and quantum simulation in the 2010s. And this particular scientific excellence translated in the John S. L. Bell Prize last year. So that founding team, they did invent neutral atom quantum computing. Today, that heritage is paired with an operational leadership to turn this science into a global business. Everyone knows this particular quote from Richard Feynman. What I want to tell you today is that for 40 years, that was an aspiration. What I want to show you today is that Pasqal is finally delivering on it, simulating nature with nature on real machines. So let me start with Pasqal today, specifically the commitments that we made and whether we kept them. When we set our plan, we made 5 clear commitments to execute and deliver on our technology roadmap, to deploy real quantum computers and make them operational in data centers, to engage customers and partners on business-relevant problems, to build ecosystems and communities around our technology, and finally, to become a truly global company. So, relatively simple to say, but let me show you where we are right now. We delivered on each and every one of them. Each commitment is now a fact, not a plan. So let me give you some concrete proof points about everything. Let me start with the result that I'm most proud of, because it answers the question that every serious person in the room is asking. Is quantum computing actually doing something more and better than classical computer can do? For decades, quantum advantage was a theoretical idea only, with the famous demonstrations that existed were done on artificial problems, not real ones. Impressive physics, but not real-world use case. What we did is different. So we took a real material, a complex magnetic material, and we simulated its properties atom by atom on our quantum processing unit. It's not a toy model of the material, it's the real thing. So here's what makes it a landmark. We didn't just produce a number, ask you to trust it, we compared our quantum simulations to the real measurement in scientific apparatus of the material. And they matched quantitatively. So the quantum computer told us how nature behaves, and then nature measured in an independent laboratory agreed about that. So this verification is everything, because as quantum machines start reaching into problems beyond classical simulation, the only way to earn trust is to check the answer, and we did. So to be clear about the advantage, some of what our machine computed would take several weeks on the most powerful GPU clusters that we can imagine. And we got that result in hours. That's the first. The second result that I want to talk about is about solving differential equations. The hard truth about quantum computing is that you have errors, and they compound. So you need to have quantum error correction procedures to actually correct for those errors in the long term. It's one of the single biggest challenges that the field needs to overcome in the future to really deliver the full promise of the technology. So what we did is that we solved differential equations on quantum physical qubits or logical qubits. And what we found is that the logical qubits gave the more accurate answer. Error correction on our machine improved the real computation. And to our knowledge, we are the only computing company in the world to have demonstrated that solving differential equations using logical qubits and doing that with better performances than with physical qubits. Of course, don't get me wrong, the system still needs to scale. The logical qubits needs to be more efficient. We are not in the regime of quantum advantage yet, but this is the road to fault tolerance. None of this is happening in the lab behind glass. Our machines are actually deployed in the field. So you can see here two pictures that are of our quantum computers that are deployed in France and in Germany, with recent deliveries that have been made also in Saudi Arabia, Italy, and Canada. Those machines are up and running, operational. You can access them 24/7. A key reason that we can do that is that we manufacture our own quantum processing units at our factories in France and Canada. And we own that capability. So let me tell you now how our quantum processing units fit in the larger computational workflow. Let me show how it fits very simply. So think of 3 layers. At the top, you have user applications where you have the customers and the users that design and submit quantum programs. In the middle, resource coordination, the middleware that bridges classical and quantum together. On that, we've been working with IBM and NVIDIA to be able to simplify the life of the end user. We don't create a new stack in parallel to what exists for classical computing, but instead, we're simplifying the life of the end user and making it easy to incorporate quantum processing units. The point is that we deliver the full stack and we integrate it to environments that customers already know and already use. Put it together now. You get 4 things. Flexible platform. The same hardware delivers analog today and FQC tomorrow, real-world results with quantum advantage in materials, as well as logical qubit computation. And you can run hybrid workflow between CPU, GPU, and QPU. Our path forward is the following. 2 major steps. First, Pasqal is going public through a business combination agreement with Bleischroeder Acquisition Corp. 2, with a Nasdaq listing expected in Q3 2026, with the Euronext Paris listing either this year or early 2027. Second, new funding of around $340 million, $400 million, split between a private financing round and convertible financing. What do we do with that? More systems, faster roadmap, broader access, and deeper customer engagement. We're building this as a genuinely global company. We're out of France with our headquarters in Paris, but we have few regional hubs, one in Canada for North America, and more importantly here, one in Seoul for the Asia Pacific. So quantum computing will be a global market, and we want to be present in all the regions that matter. In the future, here's how the value unfolds in 2 phases. Between now and 2030, we go from utility to advantage, where you can really beat classical with quantum plus HPC on hard problems in material science, chemistry, optimization across several verticals like energy, oil and gas, finance, logistics, for example. Then the second phase, the FTQC era, where you have large-scale error-corrected machines that can be used for deep molecular simulation, drug discovery, with 1,000 logical qubit use cases. The important thing is that we already generate value now, up until the end of the phase number 1, before FTQC is actually enters at full pace. What are the near-term growth pillars that we anticipate? We're executing on a set of clear pillars. First, building a global commercial presence across Europe, US, GCC, Asia Pacific. Then scaling enterprise-grade QPU manufacturing. That's really at the bottom of that particular pyramid. And driving toward industrial quantum advantage in material science and each other industry that I mentioned before, financial services, oil and gas, and energy. Each of these is already on the way, and our execution plan is clear for the next years. So, this is our vision. We're not building quantum computers to set records. We are building them to solve problems that today are simply out of reach for humanity. So take optimization, for example. Every airline, every logistics company, every power grid, they face the same kind of problems. Astronomical number of possible choices. You cannot navigate this particular solution space. Today, we approximate. It's too large to find the optimal solution. With quantum, we'll be able to find better solutions to those problems in real time. Take, for example, materials and molecules. Almost everything that limits us, batteries, catalysts, life-saving drugs, more efficient materials, it comes down to chemistry that we cannot simulate using classical computers. We have to come back to Feynman's dream. Today, discovering new material can take years with classical computers. Imagine a world where you can do that in a day using computation alone with a quantum computer. That is not science fiction. It will be hard, but everything I've shown you with the quantum advantage in materials, the logical qubits, milestones, and the machines that are running in data centers today, those are the first concrete steps onto that path. So this is a new era that we are building, new era of computing. It's not an era that is defined by faster machines, but by problems that finally become solvable. And we are ready for that. Thank you very much.